Hi, welcome back. So we're going to continue where we left off. So we want to do our boundary layer equations again, and we have knocked off some terms in the energy equation, and of course combined it with the mass balance equation or the continuity equation, just to get the order of magnitudes for the u velocity and the v velocity, or these x and y velocity magnitudes. Okay, so you can see they are very dependent upon the thermal boundary layer thickness, where we are in the so-called place. What am I talking about? Yeah, where we are, how high we are in the y direction. Okay, of course, the thermal diffusivity is one of the biggest parts of this thing. Of course, the u velocity is also dependent on x and y, because this is the thermal boundary layer thickness. Yeah, actually y. Okay, vertical height, because thermal boundary layer thickness, and I'm not going to go into too much detail here. So now we are going to go into the momentum equations. So let's try the momentum equations. Okay, now we have everything we need to scale the momentum equations. So these are our vanilla momentum equations with our Boussinesq buoyancy term here. Okay, and then we have our sort of what do you call that? Viscous terms here, and then we have our advection terms. Okay, so yeah, we can start non-dimensionalizing everything. Okay, so again, x, we'll use the thermal boundary layer thickness thereabout to help us non-dimensionalize it. We can use the momentum as well, but I'm not going to make that differentiation just yet. Okay, y boundary thickness, y boundary layer thickness, we're going to non-dimensionalize using h, and of course the u and v velocity, we're going to use these terms here in these brackets to non-dimensionalize them. Of course, this t will also need to be non-dimensionalized. We will need to use Ts minus T infinity. Remember, we have a non-dimensional temperature we define over here. We shall use this as well to non-dimensionalize the temperature term on the right hand side here. So we can start with temperature. We replace T minus T infinity with theta, Ts minus T infinity. All the rest are not changed. Then we can do the viscous forces. Okay, viscous and frictional forces are basically the same thing. I think I mistyped here. And let me put advection terms. Alright, that's a more accurate one. That's typo there. Or maybe, yeah, I wasn't paying attention. Okay, so you can see I actually non-dimensionalize u and v using this order of magnitude of u, order of magnitude of v. I have not replaced it with these yet, so that part comes later. So these are the advection terms. Then I'll do the same for the frictional forces terms, the viscous forces. Let me just type that there just to make it very clear. Okay, remember the whole reason why we are doing this is to see which terms we can just neglect. So we have not made this made all of these. I have not actually replaced all of these yet, but we can do that later. However, immediately we can already see there's one approximation we can make. You see this term inside the viscous terms. We have order of magnitude of v divided by delta t squared, order of magnitude of v divided by h squared. The rest of these two terms are non-dimensional and are order of magnitude of 1. So if we were to factorize this order of magnitude of v out, okay, this term here will be much bigger than this term here, because h is much bigger than the thermal boundary layer thickness. Okay, so immediately we can see which terms can fall off. Okay, So remember this term here, this viscosity term here is small with respect to this inside the boundary layer. Okay, inside the boundary layer. After doing that, we are just left with this expression here. Or if you want to revert it back to its dimensional form, we can leave it here. Okay. So now, are there any more terms we need to sort of get rid of? Okay. So we'll need to do some analysis before we continue. Okay. So let's start replacing order of u, order of v with all the appropriate terms over here. Okay, so the order of magnitude of u, we can just replace it with alpha over delta t. Okay, I'm not going to use this order of magnitude thing here because I mean, if both are the same order of magnitude, we can just make this statement, right? Okay, order of magnitude of u is equals to this. So that's the statement I'm trying to make here. I mean, it's pretty much the same, okay? So I'm going to replace all, wherever I see the order of magnitude of u with this term. And then, of course, wherever I see the order of magnitude of v, I will also need to replace it. So this is one thing here. And let's change the order of magnitude of v. I mean, we replace it with this thing here. So I'm going to do 1 substitution, 2 substitution, 3 substitution, and 4 substitution. And then we'll see that we are left with some terms. Okay, the buoyancy force term can never be neglected. Okay, from the dimensionless analysis, we know that this is the only term on the right. We can't actually cancel it, and it's the only driving force. From a physical standpoint, that we cannot get rid of it so easily, or at all for that matter. So, okay, all of these terms we will just combine together. In fact, you will see that all of these terms are essentially the same. You see, alpha times alpha becomes alpha squared. Alpha squared h will be in the numerator. Delta t to the 4th will be in the denominator. Same thing for this term. The h will cancel out over here. Delta t squared in the denominator. Then you have alpha squared h. Same thing for the viscosity terms. So that makes life a little bit easier for us. Okay, so let's just do that. So I have alpha squared h over delta t to the 4th. Okay, so let me speed this part up. Okay, so I'll just add this line here. See, alpha square h to delta t to the 4th, 1, 2, and 3. Okay, so we know this term, these two terms cannot just disappear. They are of the same order of magnitude, as you can see. Same order of magnitude. This term here also more or less same order of magnitude, except we have this extra new term here. Well, this is the only thing is that unless this nu is so small, which means we have an inviscid flow, okay, we cannot ignore. So for the most part, we consider most flows to have some sort of viscosity. In fact, since we are talking about laminar flow, the viscous forces will be quite significant, so we can never ignore that. Okay. So yeah, viscous forces will be very significant in laminar flow, which is the assumption that we are making in this laminar boundary layer flow. Okay, viscous forces are always significant in laminar boundary layer flow. So that applies to in forced convection, natural convection, mixed convection, whatever. Viscous forces are important, so we cannot ignore them. So this is the non-dimensional form, so to speak, and this is what we have in the dimensional form. Okay. So actually, yeah. Okay, I actually made some redundant kind of things. Yeah, I did the substitution here to find out exactly the same. So I'm going to just leave it over here. But, okay. Most importantly, yeah, these three lines are just basically what we did just now. Okay, we replaced the order of magnitude of u and v with the alpha over delta t, alpha h over delta t squared, blah 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 blah. And we collect them all together, and we see we cannot take out any more terms. So just to tidy things up, we divide both sides with this term alpha square h over delta t to the fourth. Okay, is it alpha square h? Oh, this is alpha h. Okay, I might have made a mistake here. There's no square over here. It's just alpha h. Okay, but nevertheless, we will not neglect that term. Okay, it is not safe to neglect that term. So it's not an alpha square. So my mistake, man. My mistake there. Apologies for that. So there's a nu and alpha instead on that one. Okay, so nu alpha h. Okay, nu alpha h. So that will be the term. Okay, good thing didn't delete all of this stuff off. If not, I would not have spotted my own careless mistakes. Okay, but if you want to collect all the terms together, we just divide both sides by this term here, so that we can make these two terms, order of magnitude 1, all the dimensionless terms are collected together. Very neat. Okay, and doing so, we find that we have this ratio, nu over alpha, which is the kinematic viscosity over the thermal diffusivity. What is this number? Okay, this number is none other than our Prandtl number. Okay, this number is none other than our Prandtl number, and we can see that the Prandtl number here is very important in determining whether these viscous forces have effect. Okay, it's important in determining whether these viscous forces have effect. Okay, so we'll just leave it there for the time being. Okay, so looks like these terms here are also very important. So for now, we will just leave it down there. Okay. Now the next thing we kind of want to note is the ratio. We note that this delta t to the fourth alpha square over h. Now this is a very important ratio. Okay, and we note that the Prandtl number is also very important. But if you want to know how the boundary layer thickness varies with h, then we should always know the ratio delta t over h. Okay, so this ratio, it describes the relationship between thermal boundary layer thickness and height, wall height. So this ratio is something we want to preserve. So so to do that, we just multiply top and bottom by h cubed to get the following, so that we can have this delta t over h ratio. Okay, so we can see from this equation what is this boundary layer thickness and wall height. Okay, now let's go on to the next steps. Okay, next steps actually just involve dividing throughout by the Prandtl number. Okay, if we want to leave like these terms alone, we want to divide throughout by the Prandtl number. Okay, so this will be the next steps. Okay, so I'll just divide throughout by the Prandtl number. And of course, actually before that, I want to isolate this delta t over h ratio. Okay, delta t4 over h4. Okay, it's just raised to the fourth power, so it's nothing too much there. I'll just leave them alone, so to speak. And then we'll have this other number over here. which we will deal with later. So we'll just divide throughout by the Prandtl number first. Okay, and note that again in laminar flow, viscous forces are always going to be important. We'll never neglect that. They're always in play. What's so-called more negligible are these, in comparison maybe, are these advection forces, which play a role in the momentum balance. Okay, so we'll divide throughout by Prandtl number because we never ignore this viscous forces. This is like the baseline, the benchmark, that the term that must always be there. Okay, so at least for laminar flow, this thing is always there. So we divide throughout by Prandtl number. So this Prandtl number is gone. We'll have 1 over Prandtl number on this side always. Okay. Why we have so many lines of equations is basically how I am dealing with this side. Okay. Prandtl number is nu over alpha, or 1 over Prandtl number is alpha over nu. So I'll just combine these two terms together. And I think the last line is just a duplicate of this line, which it's not very important. Okay, delta T. Yeah, I do not see any reason why there should be an extra bit of equation here. So I'll just delete this part. Okay, so here we see we see a few important numbers. One is the Prandtl number, which is very important in natural convection. The other important number is this delta T over H, which kind of makes physical sense. That's the ratio between the boundary layer thickness and the height. Then we have this other collection of terms here, which describes the buoyancy forces in relation to everything else. Okay, so what is this number called? Okay, this is one of the most important numbers for natural convection. We call it the Rayleigh number. Okay, this is this number here, just like how we isolate the Reynolds number from forced convection, and we know that's important. In sort of a similar way of importance, this Rayleigh number is very, very relevant for natural convection. Okay, but Rayleigh number and Reynolds number are not the same for sure. They describe very different things, but we know that this number, the Rayleigh number, is the important term for natural convection. In fact, this is actually the number that determines whether we have a laminar flow or what do you call that? Whether we have laminar flow or turbulent flow. So this is the differentiating factor. Okay, and remember, we never get rid of the viscous terms. Why? One is because yes, we are doing laminar flow, so viscous terms are never negligible in laminar flow. Number two, in the boundary layer, viscous terms are quite dominant, so you cannot ignore them. Okay, so this is the reason why we divide throughout by a Prandtl number. So, okay. So let's see, what does it try to describe? Okay, there are the buoyancy forces here, beta Ts minus T infinity. Then you have the height cube and G. Well, these are the beta Ts minus T infinity and G. They describe the buoyancy forces. Alpha and nu describe, I guess, how, and of course the H cube describe how the let's see. Yeah, alpha and nu describe how quickly the viscous forces and something else. Okay, it's not exactly like Reynolds number. So let's check out what the Rayleigh number. Okay, you can check out Wikipedia. It will say it's a different. Okay, according to Wikipedia, right? Yeah, is the ratio of the time scale for thermal transport via diffusion to the time scale of thermal transport via convection. Okay, it's not very obvious from here. Okay, because we derive it from a momentum balance, so to speak. But if you look at Wikipedia, you can see why that is the case. So the definition of Rayleigh number is kind of a time scale comparison. So again, the numerator, it's thermal transport via diffusion versus thermal transport, time scale for thermal transport via what do you call that? Yeah, advection, sorry. I'm getting, oh. Okay, so instead of timescales, we can equivalently take the inverse, and we can say it's the rate of thermal transport via convection versus the rate of thermal transport via diffusion. So you can see the rate of the diffusion terms are at the bottom, alpha and nu. The rate of the thermal transport terms are on top, which talk about thermal advection, okay, via advection or convection. So these are actually described by the buoyancy force terms. Okay. So I mean that's a very rough way of looking at it. I'm not trying to be accurate here. Okay. So yes, one thing you will note from this equation, if your Prandtl number is very big, okay, if your Prandtl number is very big, and of course your Rayleigh number is big enough, I mean these two terms you never neglect, you find that these two advection terms will just disappear for very fluids with very large Prandtl numbers. Okay, which means that for thermal diffusion, so to speak, okay, within the thermal boundary layer, these two terms can just be neglected. Okay. So normally, of course, these two terms cannot be neglected, but let's see why that is the case. Okay, so if you have a large Prandtl number, and that's going to be, I'm just going to zoom in on large Prandtl number fluid. Okay, thermal diffusion will be much slower than, let's say, momentum diffusion. So let's say you have over here, if you have some sort of a temperature profile, right? Temperature profile versus x. So maybe over here t is equal to t infinity. So you will have some sort of a decreasing slope. I have no idea what that slope looks like, but it should be decreasing. Okay, is Ts at the wall and T infinity at the free stream. Okay. However, something interesting happens. Okay, since there's a law of convection, so if you take a look at the U, not U, this should be V. Okay, if you take a look at the V, we notice that there will be some upflow here, and in fact here's the place where you have the biggest upflow. All right, and because diffusion momentum diffuses so well, because momentum diffuses so well in the fluid, and the fluid's viscous, the upflow here will actually carry some of the fluid outside the thermal boundary layer. Okay, so the upflow over here should, because it's furthest from the wall, so there is so-called more freedom for the fluid to flow up. I don't know exactly where this point is, the maximum velocity point or whatever, but it's a good estimate that it's somewhere away from the wall, somewhere over here. All right, yeah. Okay, or maybe the peak is somewhere closer to here. Okay, I'm not very sure, not very precise, but okay, yeah, all this velocity here, or this momentum here, is going to drag fluid outside the thermal boundary layer upwards, so that the momentum boundary layer thickness the momentum boundary layer thickness, maybe you call this delta P. This will be much greater or just greater than delta T. Okay, so actually you can see that the Prandtl number, delta T over delta P, is some function of the Prandtl number. Okay, this is very important. Okay, so yeah, the higher the Prandtl number, the larger the momentum boundary layer thickness in comparison to the thermal boundary layer thickness. Okay. Okay, so note Prandtl number is very important. Not just because we say it is, but it describes the relationship between momentum boundary layer thickness and thermal boundary layer thickness. Okay, so fraction delta T, or delta P, sorry, delta P over delta T equals to some function of the Prandtl number. So larger the Prandtl number, the larger the momentum thickness. Of course, I didn't say what the function is. We can just swap it around. I would carry around across the same meaning. Okay, it's just that I put the momentum boundary layer thickness on top, because with increasing Prandtl number, you should have an increasing so-called ratio of this boundary layer thickness. Okay, so anyway, yeah, with a large Prandtl number, we can see that within a thermal boundary layer, these advection terms are minimal. So again, if you look at this is a thermal boundary layer. Okay, over here the viscous terms dominate. The viscous terms, they will be on the order of magnitude of with the buoyancy term. Okay, viscous terms will be on the order of magnitude of with the buoyancy terms. Okay, outside here, it will be advection. Okay, it's advection, no more buoyancy term here. Advection will be on the order of magnitude of viscous terms, because over here the temperature is the same as the free stream. It's just getting dragged along by this plume, this thermal plume. Okay, so there's no more buoyancy terms here. So that's what this equation is trying to describe. It is only describing, okay, it's only describing the movement within the thermal boundary layer. Outside that, we don't really have a clue based on this equation what's going on. Okay, of course okay, well, basically in the momentum boundary layer, this buoyancy term will be lopped off. The Prandtl number will so-called come back into play, and yeah, we can have our equation back, our dimensional form of the equation back, except these terms here will just disappear, because theta would be equals to what, 0. Okay, or is this theta equals to 1? Theta equals to 0. Theta equals to 0. The non-dimensional temperature equals to 0. Then we'll just have these two forces here balance. Okay, so that's what we have for high Prandtl number fluid. Okay, so I think I've gone talking enough already. Yeah, so I'll continue more in the next video.